Alright, hello everyone. Today is day 25, the final day of Advent of Code. And today we finally hope to make it snow. But for that, we need to solve a max flow min cut problem. So what we give as input is a graph. So we have a few nodes given by the strings and the number, a set of nodes that this node connects to. And then what we want to find is remove 3 of the connections in order to split the graph into 2 different components. Then the solution would just be the sizes of those components multiplied. So how can we do that in code? So first we need to represent the graph. So we have a node which will be a string, then an edge will be a tuple of 2 nodes, and the graph will be a dictionary, represent as a dictionary from a node to a list of neighboring nodes. We can parse the input to get this representation, so we just go for each line, get a node as well as all of those neighbors, then go through all those neighbors, and to the neighbors of S, we append the T, and we also append the S to the neighbors of T. That will be useful to go through all the edges in the graph, so for that we just go through all the graph keys, and then for all the neighbors for this particular node, and then we construct these tuples of S and T. And then what we want to do in order to solve the problem is construct a maximum flow. So a maximum flow, so flow is a connection from a particular starting node to a goal node, a path. And if you wanna, and then we think of pushing liquid along this path. So if you wanna push 3 units of liquid from S from a start node to a goal node, then we need 3 distinct paths in the graph. And we construct such a flow, and then we know if there are 2 particular nodes and we can push 4 units of water along from the starting node to the goal node, then we wouldn't have to cut at least 4 connections in order to separate the start and the final node. So because we have 3 distinct paths. So we want to look for pairs of nodes such that we can only push 3 units of water along from one to the other. And that's what we do here. So for a particular starting node and a particular goal node and the graph, we find a flow. So a flow will just represent, as mentioned before, or not mentioned before, I guess a flow will be a dictionary from an edge to an integer how much we push along an edge. So this can be either 0, where we don't push anything along, or it can be 1, that we push a unit of water along, or it can be -1, which means we push a unit of water in the opposite direction. And then we also want to find the maximum flow between the start and the goal node. So there we have a loop, and we keep doing that. We try to find a path from the start to the goal, which still has capacity. So the flow is not 1 for any of the nodes. And then if we find a path, so first if this returns none, if we do not find a path, we know we already reached the maximum flow, and return the maximum flow, the number, as well as the flow configuration we found, which gives us the 3 or 4 or how many ever distinct paths from start to goal. Otherwise, if we find the path, we increase the max flow by 1, and then we go for each edge in the path and increase the flow along that edge by 1 and decrease the flow along the opposite edge by decrease it by 1, so subtract 1. Okay, so for that we need to find the path with remaining capacity depending on the current flow status. So for that we essentially consider all the nodes where you can still push water to. So the start, this will just be the start node, and in order to construct the path, then we also have this dictionary which tells us for each node the previous node from which we pushed water towards this node. And then while the queue has still elements, what we do is remove an element from the queue, and first we check if the element is equal to the goal node. In this case, we are done. I found a way of pushing water to the goal node, and what we need to do is get the path and reverse it in order to return it. So for each S, we use this previous node dictionary to find the previous node, then append this to a list of edges, and in the end we can reverse this list to make the edges in order. And in each time we take S and reset S to the previous node of S, and we do that until we reach the start node. Okay, so that's what we do if we find the goal. Otherwise, if it's not at the goal yet, we need to consider all the neighbors of the current nodes. So we consider all the neighbors as T, and then first we check if T is already in the previous nodes, which we considered it before. We don't need to consider it again, so we ignore this case. And then we also need to consider the flow from S to T. If this is already 1, then we cannot use this edge. We cannot push more along this edge, so we also ignore it. Otherwise, if T is not in the previous nodes and there is still remaining flow to be pushed along this edge, then we set the previous node of T to S and we append T to the queue. And so we do this until either the queue is empty or we find we reach the goal position. If the queue is empty, we return none, because that tells us there's not a single path from S to T, from the start to the goal, that still has capacity to push flow along. And yes, once we found this, if we found a path, we can increase the flow along this path. Otherwise, we know we're done, there's no more paths left. Right, we can solve the problem. So what we do is we want to find a node in both of the components. So we don't really know which nodes to consider. So we just go through all of them and try each pairs of nodes. And eventually one of them will be in different components. And we hope if the components are similarly sized, that will be quite soon that we find one of those. So we need to first pass the input into a graph representation. Then we go through each pair of nodes. If they're the same, we continue. Otherwise, we find our flow from S to T in the graph. And they will return the maximum value, the value of the maximum flow, as well as the dictionary representing the flow itself. First, if this maximum value of the flow is not equal to 3, that means it should be larger, then that does not allow us to find a cut. So we continue, we try another pair of vertices. Otherwise, if it is 3, that's nice, that will allow us to find a cut. So we find a cut, which will be a set of vertices, one component, which is only 3 edges towards the other component. And then the size of the first component will be the length of the cut, and the size of the second component will be the amount of nodes left, so it will be the length of the graph minus the first size. Then a solution will just be the product of both of those numbers. In order to find the cut, that's relatively similar to finding a path. So essentially what we want to know is we take all the nodes remain in the graph, but we can still push water towards, or where we still can push more water towards. So beginning, since we start the water at the start, that will be one node we can still push something towards. And then the set of visited, we also keep track of the set of visited nodes. And then what we do is just at each step, we take one node from the queue and consider all the neighbors. If we already visited T, we ignore T. Otherwise, if the flow from S to T is less than 1, we can still push water towards T. So we add it to the set of visited nodes and add it to the queue. And in the end, this will give us a set of nodes which we all can push more water towards. And then there will only be the 3 paths given by the flow, which connect it to the other component of nodes we cannot push more water towards. So yeah, and then we just consider the size of this cut and the size of the rest of the nodes, and there will be a solution. Should of course try it on the test input. That looks good, so we also run it on the real input, and it also turns out it gives us the right solution. Then for part 2, it turns out if we have 49 or 50 stars, we can start this machine and make it snow, and we collected all of those, so that's also fine. Okay, that's it for 2023. I hope you enjoyed this year's puzzles and some of the solution videos, and happy holidays, and see you.